I told you that in traditional software architecture, a 30% failure rate is, well, it's a catastrophic bug, like the kind that would have you paging the on-call engineer at 3 a.m.
Oh, yeah. You'd be panicking.
Right. But in the realm of artificial intelligence, that exact same 30% failure rate is actually the critical metric required to make a multi-billion-dollar model work.
It sounds completely counterintuitive, I know.
It really does. I mean, there is a very specific mindset we develop as software engineers, right? We live in this deterministic universe. A unit test either passes or it fails.
Exactly. A Boolean is true or it's false. There's no in between.
But the moment you start architecting large language models, that deterministic comfort it vanishes. You are no longer asking the machine if an output is mathematically correct. You're basically asking a massive cluster of GPUs if a string of text is, good.
Which is a terrifying concept for an engineer.
It is. So welcome to the late night shift. If you're a software engineer trying to map out the back end of AI systems, you are in the exact right place. Today's deep dive is pulling from a pretty dense stack of sources.
Yeah, we've got research papers on reward models, API documentation from Anthropic, and some really fascinating open source alignment repositories.
And our mission today is to dissect this crucial, highly computationally heavy layer of the AI training pipeline known as preference datasets.
Right, and to map out where this actually fits into your architecture, we kind of need to look beyond the base model.
Okay, let's unpack this. So the listener probably already understands supervised fine-tuning, right?
Exactly. Supervised learning, we feed a model massive amounts of text to teach it grammar, facts, basic syntax. But that base model is essentially just a superpowered autocomplete.
It just predicts the next token.
Right. It doesn't actually know what you want it to do.
Yeah.
So preference data sets are the raw material for the second phase, which is the human preference pipeline.
The alignment phase.
Yes. We use these massive data sets to train a separate secondary model called a reward model. And that reward model will eventually act as the loss function for the main LLM.
Which nudges its probability distributions, right? So it generates helpful code instead of just an infinite loop of gibberish.
That's the goal, yeah.
Okay, let's unpack this computationally because we need to move away from this abstract concept of teaching the AI and look at what this data actually looks like in an IDE.
Yeah, let's get into the structure.
Because in supervised learning, the data structure is absolute. You have an input and you have a target output. It's a key value pair of absolute truth.
Right.
But our sources emphasize that preference data requires a total structural pivot. It captures relative judgments. We aren't asking the system to grade a response in a vacuum anymore.
No, not at all. You're providing a prompt and then two different model-generated completions.
Yeah.
You're basically asking, hey, is response A better than response B?
Like A/B testing a UI layout.
Exactly like that. The data structure is essentially just a JSON lines file. If you open one of these data sets up, you'll see an array of objects.
And what's inside those objects?
Each object has a prompt string, a chosen string, and a rejected string. You're forcing a relative ranking.
Okay, so it's a strict binary choice.
Yeah, and by doing that, you avoid the trap of asking humans or algorithms to assign, arbitrary floating point scores out of 10. Like, what does an 8.5 in helpfulness even mean?
Right, that's way too subjective.
Exactly. So instead, you build this massive matrix of pairwise comparisons.
But mathematically, how do you capture a vibe? Because, if I'm A/B testing a user interface, I measure click-through rates, that is empirical data.
Sure.
When I'm training a reward model, how does the system process this JSON file of chosen and rejected text strings and actually convert that into a mathematical topography?
It relies on a mathematical framework, usually the Bradley-Terry model. It's used to predict the outcome of pairwise comparisons.
Yeah.
So when you train the reward model, which by the way is usually just a copy of your base LLM, but you swap out the final classification layer for a regression head.
Oh, wait, so you literally just swap the head.
Yeah. You feed it both the chosen and the rejected responses. And the model outputs a single scalar value, just a floating point number for each response.
Interesting.
Then the loss function is calculated based on the difference between those two scores. The network updates its weights to maximize the margin between the scalar score of the chosen text and the rejected text.
Okay, so over millions of rows of data, the model maps out this high-dimensional vector space where tokens that align with human preference simply have higher numerical weight.
Exactly. You're building a landscape of preference.
So it's assigning mathematical gravity to helpfulness, The model doesn't actually understand politeness. It just knows that certain token sequences consistently yield a higher scalar reward than others.
Right, based purely on that pairwise training data.
But, I mean, that introduces a massive architectural vulnerability, doesn't it? The entire backend relies on humans to generate those initial chosen and rejected labels.
It does.
What happens when the human annotators disagree on which string of text is actually better?
Oh, they disagree constantly.
Wait, really?
Yeah. The sources indicate that typical inter-annotator agreement on these preference datasets hovers between, like, 60 to 75%.
That's okay. As an engineer, if my server cluster only agreed on a network state 60% of the time, I would be looking for hardware failures or race conditions.
You'd call an all-hands meeting.
Immediately, a 30 to 40% disagreement rate in any traditional database is just data corruption. Why wouldn't we just filter out those disparate annotations and only train the reward model on the data where humans have a 100% consensus?
Well, what's fascinating here is that filtering out that variance would completely destroy the model's utility.
How so?
That 60 to 75% agreement rate isn't a bug. It's the feature that makes alignment work.
Explain that because it sounds crazy.
Think about it. If you curate a data set where annotators agree 100% of the time, you have artificially flattened the data. You are likely only feeding the model incredibly obvious, trivial comparisons.
Oh, like choosing between a really helpful Python script and, I don't know, a string of randomized punctuation.
Exactly. And so it would overfit to those obvious edge cases and completely fail to understand nuance in the real world.
So it needs the messy data.
It does. The model needs to learn the boundary of subjective preference. Human communication is a probability distribution. It's not a strict Boolean state.
That makes sense.
Right. If a user asks the LLM to write a summary of a technical meeting, one annotator might prefer a bulleted list, another might prefer a conversational paragraph. Both are entirely valid.
Right, it's just a matter of style.
Yeah. By feeding the reward model the raw 60 to 75% agreement data, you are training it to understand that natural variance. It learns to output completions that sit safely in the center of that distribution, rather than swinging wildly to extremes.
I see. So if human agreement is naturally that messy, then to build an accurate mathematical model of that probability distribution, we must need an absurd amount of data.
A massive amount.
You can't just survey a dozen people and expect the Bradley-Terry model to generalize. Where do engineers actually get this scale of human subjectivity to begin training? Let's look at the open source repositories highlighted in our sources.
Yeah, let's talk about the big ones.
Because if I'm spinning up a fine-tuning pipeline tomorrow, I need to know what to actually import into my environment.
Yeah, so the foundational library you will run into first is Anthropic's HH-RLLHF dataset.
And HH stands for helpful and harmless, right?
Correct. This dataset is critical because it mathematically encodes a very specific architectural tension.
The tension between being helpful and being safe.
Exactly. Often, the absolute most helpful answer to a user's prompt violates safety boundaries, like if a user asks for code to exploit a zero-day vulnerability.
The helpful thing is to give them the exploit. The harmless thing is to refuse.
Right. So Anthropic structured this dataset to force the model to navigate that trade-off right in the loss function. The pairwise comparisons explicitly teach the reward model to assign a lower scalar score to responses that are highly helpful but dangerous.
Establishing a baseline boundary for behavior? Computationally, that means the dataset is actively penalizing the autocomplete nature of the base model.
That's exactly what it's doing.
Here's where it gets really interesting, though. Then we have OpenAssistant, which seems to attack the data problem from a completely different angle.
Oh, OpenAssistant is fascinating from an infrastructure perspective because it relies on crowdsourced conversational trees.
Trees, not just single pairs.
Right. Instead of paying a closed group of specialized annotators, it was built by global volunteers interacting with a web interface. They didn't just rank single A versus B outputs. They ranked entire branches of dialogue. Yeah, which creates this incredibly diverse, multilingual bedrock of preference data. And that helps prevent the reward model from overfitting to the linguistic quirks of, say, a small group of paid contractors in one specific region.
That makes a ton of sense. And then there's UltraFeedback, which, from the sources, seems to address the ambiguity of the simple chosen versus rejected binary.
Yes, UltraFeedback is a major step forward.
Computationally, what does UltraFeedback look like when I pull it into my environment?
So UltraFeedback moves away from the raw vibe check. It structures the preference into a multidimensional array.
Okay.
Instead of a single binary choice, the annotator provides separate scores for specific rubrics. So instruction following, truthfulness, formatting, and overall helpfulness.
So it's not just A is better than B, it's A is better at formatting, but B is more truthful.
Precisely. And when you import this, your pipeline can calculate a weighted average of these subscores to generate the final scalar reward.
Which gives the engineer granular control.
Exactly. Say you are building a coding assistant. You might heavily weight the instruction following and formatting arrays in your loss function while completely deprioritizing conversational tone.
Because you just want the code to run. You don't care if it's polite.
Right.
That level of granular, multidimensional human data is incredible, but gathering it exposes a massive bottleneck.
A huge one. Costs and time.
Right. Human annotations simply cannot scale at the speed of compute. You're paying thousands of humans to sit at monitors, read 2 different AI outputs, evaluate them against a rubric, and submit a JSON object.
It's grueling work, honestly.
And we know what happens when software engineers hit a manual, unscalable bottleneck. They script it out.
They automate it. And that brings us to RLAIF, reinforcement learning from AI feedback.
Right.
We've reached the point where generating synthetic preference data using AI judges is a viable, mathematically sound alternative to human annotation.
Okay, I'm going to need some technical proof here, because using an LLM to generate the data that trains another LLM sounds like a catastrophic feedback loop.
Sounds like a recipe for disaster, yeah.
If the judge AI is just an LLM, won't it over-index on its own statistical quirks? We've all seen models that overuse words like delve or testament.
Oh, delve is everywhere now.
Exactly. So if the judge model prefers those specific token sequences and it evaluates millions of generations, aren't we just automating mode collapse at compute speed?
Well, if we connect this to the bigger picture, mode collapse and bias amplification are the exact failure states researchers monitor for. You don't just prompt a base model to pick the best response and let it run wild.
Okay, so how do you constrain it?
The mechanism requires a highly structured hybrid architecture. First, you take a very capable large parameter model to act as your judge.
The smartest model you can afford.
Right. And use a complex system prompt that includes the exact scoring rubrics from datasets like UltraFeedback.
So you force the judge model to output a reasoning trace before it outputs the final score.
Chain of thought is mandatory here.
Yeah.
You prompt the judge model to generate a JSON object containing an analysis of response A, an analysis of response B, and only then the file chosen or rejected flag.
It has to show its work.
Exactly. And to prevent that echo chamber effect you mentioned, engineers anchor the judge model.
How do you anchor an AI?
They validate its outputs against a pristine human-annotated dataset first. If the judge LLM's pairwise preferences correlate with human preferences at a high rate, say, matching that 70% human consensus mark, then you have mathematical confidence that its reasoning aligns with human baseline variance.
Wow. So once it's validated against the human baseline, you just unleash that judge across a cluster of GPUs to evaluate tens of millions of generations.
Yep. It is purely an infrastructure play at that point. You are trading expensive human annotator hours for cheap GPU compute hours.
Which leads directly to the core architectural dilemma our sources map out.
The budget question.
Right. Given a finite project budget, do you allocate your resources toward acquiring a smaller batch of high-signal human data, or do you burn your budget on compute to generate a massive volume of synthetic AI data?
So the sources outline very clear scaling laws for preference data quality, and it is an entirely nonlinear relationship.
Meaning it's not just a straight line graph.
Not at all. When you are initializing a project and your dataset is small, perhaps just a few thousand JSON objects, data quality is your primary bottleneck.
Because every data point matters.
Exactly. In a small data set, every single mislabeled pair or noisy comparison actively degrades the reward model's loss function. At this stage, you allocate budget to expert human annotators. You need artisanal, high-signal, low-noise data to set the foundation.
But the math inverts as you scale up into the millions of parameters, right?
Dramatically.
Yeah.
As you scale the dataset size into the tens of millions of rows, sheer volume begins to act as a regularizer.
How does volume fix bad data?
Well, if you have 10 million pairwise comparisons generated by a synthetic judge model, and say 5% of those are hallucinations or low-quality labels, the sheer gravity of the correct data overpowers the noise.
The gradient descent process will just smooth out those anomalies.
Exactly. It washes out the noise.
So what does this all mean for the engineer? Chasing perfect human accuracy at a massive scale yields diminishing returns.
Right.
If I spend my entire budget trying to get perfect human curation on 10 million rows, the resulting reward model won't perform significantly better than if I used a massive volume of good enough synthetic data.
It's a waste of resources at that scale.
So the optimal backend strategy is to seed the model with pristine human data to establish the vector space, and then shift to massive automated RLAIF generation to build out the scale.
You manage your compute budget by understanding exactly where quality stops mattering more than quantity.
That is incredible. Well, we have dissected a massive segment of the AI backend today. We started by looking at the structural pivot away from absolute Booleans to the relative JSON-based pairwise comparisons of preference data.
Yep.
We explored how the Bradley-Terry model converts a simple A versus B choice into a scalar reward score, basically mapping a topography of human values.
And we examined why a 60 to 75% disagreement rate among humans is necessary to capture the probability distribution of natural communication.
Right, which prevents the model from overfitting to artificially flattened data.
Exactly.
We pulled the documentation on the major open source repositories, Anthropic HH, OpenAssistant, and the multidimensional rubrics of UltraFeedback.
We look at how engineers bypass the human bottleneck by implementing RLAIF.
Using validated judge models to output reasoning traces and synthetic labels at compute speed. And finally, we mapped the nonlinear scaling laws that govern whether you should spend your budget on human accuracy or GPU volume.
This entire pipeline is the prerequisite infrastructure. I mean, it is the raw compute and data engineering required before the LLM you use every day can write a single, helpful line of code.
Which leaves us with a really fascinating architectural tension to consider as you switch back to your IDE.
Oh, absolutely.
We established that human agreement naturally caps out around 60 to 75%, and that specific messy variance is what prevents a model from becoming a sterile autocomplete engine.
Right.
But we also established the economic necessity of scaling up using synthetic AI judges to generate millions of data points.
And this raises an important question. If we rely on AI to generate the bulk of the preference data that trains the next generation of AI, are we mathematically ironing out the very human variance that made these models useful in the first place?
That is a wild thought.
Even with chain-of-thought prompting and hybrid anchoring, as the volume of synthetic data overwhelms the foundational human data, we might be slowly trading the authentic probability distribution of human preference for the clean, predictable, but ultimately artificial efficiency of a judge algorithm.
A tension between the scale of our compute and the reality of our humanity. Thank you for joining us on this deep dive into preference datasets. Keep questioning the architecture beneath the abstractions, keep optimizing your pipelines, and we will catch you on the next one.